Thank you. We started talking about feedback systems last time, and there was an example that we ended up rushing through, so I want to make sure we have that nailed down properly. Here's a filter you've seen, one-sided exponential. We've figured out its frequency response in the past, and then when we looked at the magnitude response, remember I wrote everything in the numerator and denominator in terms of non-negative powers of e to the I omega. Because then when I look at the expressions, I'm looking at vectors in the complex plane. So I take the magnitude of the frequency response. The numerator is 1. You can think of this as e to the I omega minus 0. So there's a 0 here with a vector going toward e to the I omega. But as I go around the unit circle, the length of that vector doesn't change. It always stays 1, so it doesn't really influence the magnitude response. And that's specified up here when I take the magnitude. So the vector that does matter is this one in the denominator. E to the I omega is where I am on the complex plane. 1/2 is where I've drawn the x. And e to the I omega minus 1/2 is that red vector. You've seen this before. And as we go around the unit circle, the magnitude response changes according to the inverse of the length of this red vector. So the red vector is shortest when I'm at 0. It's longest when I'm at pi, or minus pi. And that's why the magnitude response is the smallest when I'm at those high frequencies, and it's the maximum when I'm at 0. Now, how does feedback come into the picture? Suppose you've built 1 million of these gadgets, and your boss tells you, OK, I want a high-pass filter. Can you build me a high-pass filter in a way that we won't let these go to waste? You say, sure. Let's see if we place that system in a feedback where the feedback is, I'm going to denote it this way, alpha z to the minus 1. Or what did I use last time? Beta, I think I used beta. Beta z to the minus 1. This basically combines a delay. A z to the minus 1 is a delay. I mentioned this in a previous lecture. Followed by a beta. So that's what this is. And I send it through. Did I put a minus last time? Let's stick with, No? That can't possibly be controversial. There are things that deserve to be controversial, and there are things that don't. Just look at your notes. So I did not put a minus sign. I did not. Maybe I should ask the people at home. OK. So what is the frequency response of this feedback configuration, if we call that h? Let's not put the omega inside the system. Let's just keep it by its name. So what is the frequency response of the overall system? Forward gain, which is omega, over 1 minus the loop gain. And what's the loop gain? Well, G is in there. What else? Beta e to the negative I omega. E to the negative I omega is the frequency response to this. OK? So now I have the expression for G, and I have the expression for the overall frequency response. Let's plug it in and see what we get. So I have 1 over 1 minus 1/2 e to the minus I omega over 1 minus beta times this over 1 minus 1/2 e to the minus I omega. And I obviously have to take a common denominator so that I can get rid of this and this. So we get 1 in the numerator And in the denominator, what do I have? 1 minus beta plus a half e to the minus I omega. So this is the frequency response of the feedback system. This toggle beta and the storage element now enable me to move the location of that x. If beta is real, what's the set of locations that I can move the x to? -1 to 1. Right? I don't want to go outside the unit circle for reasons that you wouldn't know at this point. Well, actually, you would. The reason that x doesn't go outside the unit circle is that if you have a number larger than 1, when you plug that g into the frequency response infinite sum, it's going to blow up. So that's why I want that exponential to always stay within the unit circle. And if it's real valued, that means it's got to be between -1 and 1. So this beta, subject to that constraint, enables me to move that x from +1 to -1. Okay? Suppose I want to make the peak sharper. Where would I want to move that x to? Closer to 1. So this is now the kind of thing that I mentioned in a previous lecture, design-oriented analysis. You're analyzing this filter, but with design as a goal. So to sharpen the peak, at omega equals 0, we move the x closer to 1. So beta has to be between what range then? Beta goes toward 1/2. But you don't want it to reach 1/2. Okay? So that's one way you can use the feedback system to change your design. If you want to make it less sharp, you move it closer to 0. Now, the other question that I started the lecture with is to make a high-pass filter out of this. We move the x to where? The x to where? To negative values, to -1 and 0. If we want a sharp high-pass filter, we move it closer and closer to -1. So you've got this knob. And all you're doing is grabbing a piece off the shelf, something that's already gone into production. You've got 1,000,000 of these. And the only thing you've got to add is a storage element and a scalar amplifier. And you put it in this configuration, you've built your new filter. You may even have a box with a knob that adjusts this beta. Okay, so this is one application of feedback. And feedback has many applications. I'll give you one for analog systems. Another application. And that's to design an inverse system. let's say you have an audio signal that goes through, actually let's say we're in a room. I'm speaking, and you hear some version of what I'm saying. What you hear is a sum total of all the reflections of my voice from the walls. All kinds of things are happening before they get to your ear. In fact, each of you will hear a different version of what I'm saying. Hopefully positive doesn't become negative and so on. But suppose sitting at a particular location, you have a model of what happens to my voice before it gets to your ear. And suppose we simplify everything and model that process with an LTI system. So I speak, my sound goes through an LTI system. What you hear is the output of that LTI system. So that LTI system is the model of what happens in the room. But you want to hear something as close to what I'm saying as possible. So you want to have a system right before the sound goes into your ear that would undo what the room has done. So here's my voice. This is the sound of my voice. It goes through some process. What you hear is V. And you want to undo what happens, so you get X back. Okay? Or suppose my voice has been recorded, and you want to process it to recover what's happened. Or suppose this represents noise that's entered the signal, and you want to undo it. For whatever reason, you want to design an inverse system. Well, feedback enables you to do that. In this way. Let me see if I have a plus sign yet. I have a plus, minus. X goes here. Y comes out. This, by the way, I use the letter P for this because in feedback theory, this is called a plant. Something. P, the system P. Feedback theory. Or in dynamic system theory in general. So this is usually called a plant. Plant is something you really don't have a control over. The best you can do is model it. And so you stick a model of it right here in what you're designing. And you stick that model in this feedback configuration with K as a constant gain. Okay? What's the frequency response of this feedback configuration? Figure it out. Is there a question? This is continuous sum. Doesn't matter. So this should have taken a total of 30 seconds to do. Meatball. Sandeep, go for it. H of omega is Black's formula, which is what? K over 1 plus K P of omega. Okay? Why don't we have a minus? Because of the minus. So this minus becomes like a constant gain in this loop. Forward gain over 1 minus the loop gain. Loop gain is K times P times minus 1. Minus that turns it into a plus. Now, here's the gimmick. If I make Kp much larger than 1, what's going to happen? If Kp is much larger than 1, what can you approximate H2? So take me through the steps. This is much greater than 1. So what do you do with the 1? Get rid of it. So you're left with K over Kp. And then the K's cancel. So you've approximated an inverse system. Okay? Not exact, but we usually have in the real world some tolerance for going away from the ideal. As long as it's a good enough approximation, we're happy. Okay? Now, here's the great part of this. Kp doesn't have to be much greater than 1 for all frequencies. All we want is for Kp to be much greater than 1 over the frequency range of interest. That makes life a heck of a lot easier. Okay, so that's one point. This need only hold for the frequency range of interest. Now, when you're trying to design these analog systems, you bump into some real-world constraints. For example, it's very hard to build a system that has a high flat gain over a wide range of frequencies. It's hard. You can make a flat gain over a short range of frequencies, but to make a flat gain over a large band of frequencies is hard. That was one of the big problems that plagued analog audio for years until this digital came in. The whole competition was who can make the flattest, widest band audio filters. That was hi-fi. Okay? Now, the great thing about this is that K doesn't even have to be flat. It doesn't even have to be a constant. All you want, let's suppose this is not a constant. As the frequency changes over the range of interest, K is actually a function of omega. You can make this a function of omega. It doesn't matter that K is not a constant. As long as the product of K and P is much greater than 1, and you can get rid of 1. So I said you can make something flat over a small range of frequencies. If you want to go over a wide range of frequencies, you got to let something give. You've got to tolerate some change in the constant. It's kind of like you can fool some people some of the time, or most people most of the time, whatever it is. Can't fool me again. So K over the range of frequencies needs to be high so that Kp is high. But it doesn't have to be flat. because the flatness of it is not what enables you to do the approximation from here to here. It's the fact that the product is much larger than 1 that enables you to do that. And that's what's great. So you can make it large and let it roll off. So what? As long as the product is large over the range of frequencies, you've designed your inverse system. So these are just 2 examples of feedback systems that I wanted to talk about. I believe in one of the problem sets that are coming up, you have other examples. I think I have a discrete time system example of this. Let's take a 2-minute break, and then I want to talk about causality and memorylessness, so you can do your problem set. Okay, people. The what? Oh, midterm, we're going to do it in this room. And the what? When do you want it? I'm at your service. No. Listen. I'm going to let you have Tuesday free. Actually, no, it is a holiday. No, no, no. Holiday is the week after. Election day is not a holiday. So I'm going to let you have Tuesday free. Because I want you to go and stand in line and vote. I don't care how you vote. Just go and vote. So I don't want you to have any excuses. And so we're not going to put the exam on Thursday, because then a bunch of you geeks are going to be sitting at home using the exam as an excuse not to go vote. So how about having the midterm the week after the elections? So exactly, the 11th is a holiday. Hold on. The 11th is a holiday. That makes it the 13th. So mark your calendars. 13th, in-class, midterm. Now that I made myself popular, I'm going to tell you that in about 9 minutes, I'm going to make myself very unpopular, because you're going to have a quiz. Didn't we do that? That was on the first. Okay. Causality. Causality is very straightforward. A causal system is a system that does not have to wait for future inputs to produce the output now. It's a system that does not peek ahead. It only uses the values of the input signal at most up to the current time, and it uses past values of the input. So the colloquial description is a system that doesn't peek ahead of the input. In other words, y of t depends at most on x of tau for tau less than or equal to t. That's basically what it is. Y of t, for example, does not depend on x of t plus epsilon, or epsilon is a positive number, or t plus 1 second, or half a second, or even 1 microsecond. So to produce the output at any given time, the system only looks at the current or past values of the input. X of tau. That's a dummy variable. So it depends on all the x of taus for tau less than or equal to t. Or in discrete time, that's the description. Okay? Now, the more mathematically minded always have to make things complicated. So they have a more precise definition. Actually, that's precise enough. But the other definition is that if two input signals, x1 and x2, no, this is good. If x1 and x2 are equal up to a certain point in time, so here's t, here's x1 of t, and x2 of t is this one. If a system is causal and you apply these two inputs separately to it, And these two for all t less than or equal to t naught. And up until some point in time t naught, these two input signals are the same. A system that is causal is not able to distinguish between these two because it's not looking ahead. It's not noticing that these two will diverge from each other in the future. So the response corresponding to the first input and the response corresponding to the second input must be the same for all t less than or equal to t naught. Okay? If this is true for a system, for all, if the above is true for all x1 and x2 in the input signal space. Remember the input signal space? And the output signal space. And, whoops. And for all t naught, then the system is causal. The system, let's call it F. F is causal. So it's not sufficient that just for one pair of signals or for just one such time instant this property holds. This property must hold for all such pairs of input signals in all such cutoff times t naught. So if it's, now obviously this is not a practical way of testing whether a system is causal. It's a way of showing that the system is not causal. If you want to show that a system is not causal, all you have to do is find two signals that are identical up to a certain point in time. Are the corresponding responses equal up to that time? If the answer is no, you can rule out causality. Okay? System doesn't peek ahead. So when it's going about its merry way, figuring out the outputs as we progress in time, it doesn't know that these two are going to be different in the future. So the response it produces for x1 and x2 are identical up to this point t naught. Okay? Now, with LTI systems, this translates into something very simple. Causality for LTI. Systems. I'll do it for discrete time, because that's easier to see. The output is always the convolution of the input and the impulse response. So this m goes from minus infinity to infinity. You want to make sure that no values of the input in the future relative to n is included. How do you ensure that? You don't want the system to look at any value of the input in the future. What ranges of m should I eliminate? M less than 0. Because when m is less than 0, let's say m is minus 1. If I write this out, I have h of minus 1, x of n plus 1, plus h of 0, x of n, plus h of 1, x of n minus 1, plus dot, dot, dot. So it's this one and all the terms prior to it that will pose a problem if I want this system to be causal. So an LTI system that's causal must have an impulse response that is 0 for negative. So for this to be causal, we must have h m equals 0 for all m negative. Any LTI system whose impulse response is 0 for negative time instants is causal. The same is true for continuous time. H of tau equals 0 for all tau less than 0. Instead of the summation, you have the integral. So an LTI system is causal if and only if its impulse response is 0 for negative values of its argument. Let's do one example, and then we'll break off for the quiz. Here's a system that I partially describe. 1, 2, 3. 0, 1, 2. 1, 2, 3. And the corresponding output is, so this is x1 of n. Oops. And the corresponding output is 2, 1. That's 0, 1. So this is y1. And if I give this system the input 2, 3 at 2, 3, the corresponding output is -1 and 2 at 0 and 1. Can this system, this system is also known to be time invariant. So I tell you that much. I tell you that this system is time invariant. And I tell you when I give it this input, 0 everywhere that I've not drawn anything, I get this output. When I give it this input, I get this output. Can this system be causal? Da, 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 da. Let's get this done. Come on. 2 minutes is not going to save you from the gallows. Who says yes? Can be. I hope nobody says must be, because I haven't completely described the system. So it's either can be causal or cannot be causal. Can be causal. Okay, you're retracted. Wish politicians would do that. Cannot be causal. Ooh, you go for it.
Since in the case of x2, you have an output that is, the output is produced at points before an input is even supplied.
Oh, I love this. Yeah.
So it can't be causal.
Now, this is very plausible. Like the kinds of arguments that politicians give you, it's always plausible. And it works for this particular case, but it's an insufficient argument for the time being. Because here's the deal. I give you a system that no matter what you give it, produces cosine omega naught n at the output. Whatever you give it, it produces this. Right? Y of n equals cosine omega n for all x. This is a perfectly causal system. Doesn't look ahead. But if I give it, let's say, this input, it certainly precedes the input signal. It has non-zero values before this one. So that by itself is not sufficient. It turns out when you have a time invariant system, then your argument holds. but we'll do more of that in the next lecture. So the best thing you can do here is say, okay, this system is time invariant, so I know what the response is when I shift the input. Shift this input from 2, 3 to go down to 1, 2. Okay? Shift it by one sample. What happens to the output? You shift it to the left by one sample. Now, after you shift this to the left, x2 of n plus 1. Let's call that x3. y3 will be minus 1, 2. Okay? Now notice x3 and x1 are equal for all n less than or equal to minus 1. Do you agree? Yes. Are y3 and y1 equal for all n less than or equal to minus 1? No, right? But y3 at minus 1 is not equal to 0, which is y1 at minus 1. So this system cannot be causal. All right, let's distribute the quiz. We'll do more of this in the office. I will hold office hours tonight. So come on over.